Hello, everyone. Recording is in progress. Welcome to our class today, Thursday, February 3rd, 2022. We'll continue where we stopped yesterday. There is a couple of things. The first thing, who would volunteer to answer the in-class practice? Okay, the first one was Alex. Unmute your mic and share your screen and go ahead.
Yeah, sure.
The others, keep your hand raised up, so we might also look for your answers.
Sure. Can you see my screen?
Yep.
Yeah, so I think it was the bottom one here. So basically I had any string where any single symbol was repeated one or more times. So this one here, since it copies the same notation. So that was my best crack at it.
Mm-hmm. Okay, let me record your participation. Extreme. Okay. Alex. Okay, now the second one is Tony. You can share your screen and go ahead.
Sure, yes, let me just do that. And am I answering the same question?
You can answer the same question or the other question.
Okay, yes. I still wasn't able to figure out the other question, but yeah, for this question, I think Alex did it pretty well, but maybe I'll just like clarify a little bit. So yeah, so sigma could be any symbol. And in this case, it could be repeated one or more time, but they must be repeated one or more times as a pair. So here's an example. Say that F is sigma. You could have FF, but you could also have 4Fs or 6Fs, 10Fs. They just have to be an even length because you have to be able to form it with two of those symbols. So that's the only requirement, but it could be any symbol. So it could be 1, it could be 0. They just have to occur in multiples of 2.
Thank you. Thank you, Tony. Questions to Tony? Okay, Gareth. Thank you, Tony. Gareth, you can share your screen and go ahead.
Sure. 1 second. I think for this question was asked, or I think Tony asked about this question at the end of last class.
Yes.
Okay. I'm just going to change my screen share though to a picture of something I did. I'm not sure if this is right or correct at all. But I opted to like write out what that statement would mean in like as a regular expression. And we know that like if there is a regular expression, then there must be a unique language that corresponds to it. This was just in the class notes.
Mm-hmm.
And then therefore, because there is a unique language that corresponds to it, we know that there has to be a DFA because there exists a DFA that, or yeah, for every language there exists a DFA. I'm not sure if that's a sufficient proof for that question though.
Okay, thank you a lot. Thank you. Now, I'll answer this question now. When he mentioned there is a DFA for every language, does that count for irregular language? What do you think? It's only for regular language, Brandon. Okay, so let me share my screen. Gareth, can you like mute your mic, please? Okay, thank you. Can you see my screen? Yes, sounds good. Thank you, Longi. Now, the question was, show that for each or every DFA for LKW belong to 0 and 1 star, the kth last bit is 1. So, base case, where is the second last bit must be 1, k equal 2. Because here we don't know k. So, if we assume that k is equal to, so here whatever 0 or 1, here must be 1, then whatever zeros or 1 for the remaining. So if we ask k to equal 2, so this one state will be reached only if we receive the 1. Now, if k equal 3, if k equal, like here, general cat must be 1, third k or third last must be 1. And if you go to the kth, this is the DFA for it, 0, 1, 1, which is, this is the kth position, 0, 1, 0, 1, q to q, q2 to qk minus 1, whatever they are, zeros or 1, this should be a 1. And here is the answer for the another question, is a regular expression that consists of a regular language repeated 2 times. Same as your colleague answers. So here, we don't know this one. It depends in the question, what is the k? How we decide the k. Okay, guys? What is the k? Okay, now we'll move to the pumping lemma. So, non-regular languages again. I thought that a DFA, it is determined. It depends on the question. What is the value of k I gave to you? Okay. In the exam, I'll not give you like unknown k. Okay, Turney, you're asking what a question. This is for the third class. We ask to answer this question. Volunteers, no one volunteer except the last student who tried to answer it, who's Gareth. It is in class note number 5, page, I'm not sure what page it is, page 3, beginning of page 3. Class note 5, beginning page 3. Okay, thank you. Okay, so we said for non-regular languages, there exists a non-regular language. Non-regular language typically require us to maintain some count. If we need to maintain some count, and you know that deterministic and non-deterministic finite automata, we don't deal with memory yet. So at that point the language would be not regular. How to prove that the language is not regular? As we mentioned yesterday, we will use pumping lemma. Pumping lemma depends on pigeonhole principle. What is pigeonhole principle? If I have n plus 1 pigeon and I have n holes, and all pigeon accommodated in a holes, that means there is one hole that has more than one pigeon. We discussed this yesterday. Today we'll go with more example to be familiar on how we will do the proof. Okay, tomorrow we'll release first assignment. First assignment has pumping lemma question. In the midterm, you'll have pumping lemma. In the final exam, you'll have pumping lemma. So please concentrate, not let me move to the next step if you don't understand the current step. Okay, guys? So again, we will repeat the pumping lemma theory. If L is a regular language, then there exists P, which we call it pumping length, which is P, which is greater or equal to 0, such that for all string W belong to L, where the length of W is greater or equal to P, and there exists a partition of W to be partitioned to 3 parts, X, Y, and Z, where the cardinality of XY is less or equal to P, and the cardinality of Y could not be a 0. And for all I greater or equal to 0, such that the string will be XY to the power IZ belongs to L also. At that time, the language is regular, if we can pump Y. If we cannot, or the resulting string of pumping Y is not belong to that language, or will not satisfy the constraints or the conditions of that language, that means the language is not regular, or the expression is not regular. So we use pumping lemma to show that a language is not regular. So if A will lead us to B, then not B will lead us to not A. This is, we call it contrapositive form, the contrapositive form. The contrapositive form of pumping lemma is let L included or equal to alpha star or clean star if all P greater than 0, openent, there exists W belong to L, that the cardinality of W greater or equal to P. This is your assumption, such that for all partitions W, X, Y, and Z, this is the openent. The cardinality of XY is less than P or equal P, and the cardinality of Y is greater than 0. Then it becomes your part again for each I greater than 0, such that XY to the power IZ not belongs to L. This is your, then L is not a regular language. This is like show you the steps. These are the openent. It's by definition. These your parts that you will work on to have your proof complete. Okay. Now we will have an example and show that the language is not regular. From now, I'm telling you yes. As we said, why we use pumping lemma? We are checking, we put the properties of regular languages, and we are trying at one of your side, because I told you it's 4 steps in the proof. 2, they are there always, and 2 are yours. So we are trying by those 4 steps to prove that the language either satisfy the 4 things, then it's regular, or we negate one of them, that means it's not regular. So this is what we are saying here, the contraposition form. If A lead to B, then not B will lead not A. So if there is not here, then it's not regular. Did you get that? Okay. So back to our example in the handout, the first example, that L equal O to the power n1, 0 to the power n1 to the power n, where n greater or equal to 0. That this string, that the number of ones and number of zeros should be the same. So at the beginning, giving P greater or equal to 0, that we would assume that the pumping length is greater or equal to 0. This is the open-end move. Then we will choose that W equal O to the power P, 0 to the power P, 1 to the power P. This is your move. Now, given a partition, we would say that W could be partitioned to X, Y, and Z, where the cardinality of X, Y is less or equal to P, and the cardinality of Y is greater than 0. Note that these string X and Y consist only of zeros, open and close. So this is how I choose it, that the Y is part of zeros. This is your move. You can use it part of 1. You can use it 0, 1. You remember the cases that we studied yesterday in the example? These are the cases. Here, for me, I would assume that I'm in the exam and I would solve it. So I choose that X and Y, they are zeros. So the string Y will take part of the zeros, and I will leave the ones for Z. Now, choose I equals 0. I will start testing. Then X, Y to the power 0, Z equal XZ, because Y to the power 0 is 1. So O to the power L, 0 to the power L, and 1 to the power P, where L equal P minus the cardinality of Y, and this is not equal to P. So X, Y to the power 0, Z belongs to L. So since I have different zeros and 1, is the language regular? No. So here it's not belong. Guys, I forget to put the cross here. This one should be not. Here should be not. Example 2. Assume that we have a language L2 that consists of A to the power L, B to the power M, C to the power N, where L plus M less than N. What does that mean? That means that the AB count should be less than N. From here, yes, if you find with I, Y to the power I, one of them prove that it's not belong to the language, that's it, you're done with your proof. What we have yesterday, I clarified this at the class, you don't need to test all the cases. But we try to show you different cases because I don't know in the exam, you or your colleague, how you will partition your string. Is that clear? So here, again, giving P, I leave it empty. You should put it same as here because this is always there. So you have to add it yourself. Given P greater or equal to 0, open up move. Choose W, A to the power P, B to the power P, C to P. This is your move. Why I choose that? Because we said L plus M is less than or equal to N, which means that the maximum that L and M are equal, they will form, like if N equal to I, then this will be I and this will be I. Here we use the P, so P, A to the power P and B to the power P. Based on this condition, then N will equal 2 P's. This is your move or my move in the way I solve the question. Given a partition, W equal X, Y, and Z, such that the cardinality of Y, XY less than P, and the cardinality of Y is greater than 0. This is a condition and it's fixed for all the question. So this one, you don't have to change anything when you answer your question. This one, you don't have to change anything when you answer your question. Your work will be in the second step and in the last step. Okay. We have Y equal A to the power T for some T greater than 0. So then X, Y square, we choose I equal to X, Y square Z equal A P plus T, B to the power P, C to the power 2P. Then the cardinality of A plus the cardinality of B is greater than C, because we add here T when we pump the Y, because we choose the Y to be with A's, part of A's. That's why you see here, this is what I mean. We have to cross it to be the same as here. Then XY square Z not belongs to L2, then L2 is not a regular language. Why it is not a P plus 2T? No. Hold on, Ardia. I said we will choose Y to be part of the pumping. So X and Y, they are at the A part. B and C, they will be in Z. When we set A to the power P and I pump it, I assume that the pump is to the power T. So it's not square. Why you square it? So Y square, it's a part of A's, not all A's, because part of A's will be for the X or for the original A's. Okay. Any other questions? Any questions for example 2? Let's go to example 3. We would assume that we have a language L3 that has a string W that belongs to 0 and 1 star. Number of zeros in W equal number of ones in W. Okay, Jenny, I'll go back. After answer example 3, I will repeat example 2. Okay. So, using regular properties, closure properties. Hi. L equals 0 to star, 1 to star, intersect with L3 equal L1 in example 1. Here. Because it's the same as this one, but here we make it stars. If L3 is regular, then L1 is regular. We have shown that L1 is not regular. So by contradiction, here, there is L3 is not regular. So here, for example, if you receive something, assume that we have 0 to the power n, 1 to the power n, and prove that that's 1 is not regular, then 0 to the star, 1 to the power star is not regular. Now back here. Here we have based on the language, we have A's, B's, and C's. And we said that the maximum that C or M could be, which is, if those are equal, it would be 2 of those. So we said A to the power B, P, B to the power P, and C to the power 2P. Now, I need to do the partitions. The partition I choose that X and Y are belong to A's, then Z will have the B's and C's. Clear till here? And we know that at the beginning we have A to the power P. So when we pump it, these pumps, 2, 3, 4, whatever the value of I choose, it will be added to P. We use T to represent that. So A to the power P plus T is not equal, the number of A's will not be equal to the number of B's. And the total number of A's and B's will be more than the number of C's. So here the language is not regular, because we said here L plus M should be less than N, but when we pump it, it will become more than N. Is that clear, Jenny? Okay, good. So here we said L intersect L prime equal L double prime. What does that mean? If L is a regular and L prime is not regular, it does not imply that L double prime is not regular. So if this language is regular and this language is not regular, and the intersection, the shared thing, which we represented by L double prime, it could be a regular or not, we don't know. We cannot generalize the rule. If L and L prime are non-regular, even then L double prime may be regular also. Maybe the shared thing between two non-regular language would be a regular language. So we have to prove and see if it's regular or not. Now, if we have a language that consists of 0 to the power P, where P is a prime number. So this question, I use P here to let you know that you can call the pumping length. Normally we use P, but you can use X, Y, Z, L, D, whatever you want. That's why we use in this example, it's a P, and here we make the pumping length name Q to show you that it's, if you didn't put P, you use any letter, that would be okay. Given Q greater or equal to 0, we choose W to equal O to the power R, where R is a prime and greater or equal to Q. Now the partition X, Y, and Z, where Y equal T, we choose I equal R plus 1. Here we don't assume a symbol, we assume an equation. So then X, Y to the power I, Z equal O to the power R plus I minus 1 times T. And this would lead us to R plus RT. Then 0 to the power R, 1 plus T, which is not a prime. So it's not belong to L4. L4 is not a regular language. So you see, most of the question we solve it the same way, but it depends how we will proceed in partition the equation or the string. How you would partition, then you will arrive to step 4. Questions? Guys, I'm not here to teach you math. R plus R. When we talk a shared R, then it would be here 1 plus T. This is a basic math principle in how to deal with power. No need to be sorry, but these are basic like power operation math. You know, we talk R as a shared, then it would be R times 1 plus T instead of the other R. Because we have R at both sides. So R, then here 1, and R here will go to R, then it will be 1 plus T. Okay. Any other question? Okay, let me stop share. Okay, guys, there is an issue that I've been told by your colleague, I think Austin. Thank you, Austin, for bringing this in. That there are some students who has in-person classes right before our class. Then they don't have a time to find like a venue or a place to sit to attend the class. For today's class, it's quite difficult to delay the class. And because, you know, it's a 1 hour class, it's 50 minutes with the break. So it's quite difficult. But for Wednesday, I'm not sure if you guys would like what time we start on Wednesdays. It's 10:30, right? Ten 30 to 12:30. So if you would like, we could start at 10:50. 10, which is 10 minutes to 11. So I give it 20 minutes for those to move to certain place, to library, to put your headphone and attend the class. You know, this is the best I can do. Or we can stay at 10:30. We started at 10:30, then we finish earlier. What do you prefer, guys? I'll take voting. Let's say the first thing that we will stay the same. We start at 10:30. Okay, Amanda, you have a class at 12:30, which means if we delay it and finish exactly at 12:30, it would be difficult. Okay, let's make a vote about this. What about to start at 10:45 and end the class at 12:15? What do you think? So okay, it seems that would fit everybody. So as of next Wednesday, I will send an announcement and I will change the Zoom timing, that our class will start at 10:45 and we will end. I'll make sure to end before 10:15. Always, I'll make sure to like end it at 12:10 to give you like 20 minutes to move to your next class. So that's good. I'll send the announcement. Tomorrow, I will release assignment 1. Guys, and next class, I don't think we're gonna start with a new handout. Let me see what is next. We're done with handout 4, completed, yes. Then handout 5, which is context-free grammar. Then we'll back to again pumping lemma later. But I will. Okay, let's start with handout 5A because it's related to our topic today. So we'll be done with these things. Oh, but I want to make sure that it's in there and all resources handout 5A. Yes. Zero. Okay, it's very quick, and that will take less than 10 minutes. I'll share. Yes, this handout added to the material. So we'll talk like briefly about proof technique to let you understand what is the mathematical induction, what is the pigeonhole, what is the contradiction, the types of proofs. Mathematical proof. So proof technique. In mathematics, a theorem is a statement that is a true. A proof is a sequence of mathematical statements that form an argument to show that the theorem is true. The statements in the proof of a theorem include axiom assumptions about the underlying mathematical structure, hypothesis of a theorem to be proved, and the previously proved theorem. So sometimes I have assumption, sometimes I have a previous proved theorem that since that one is approved, then I can use it in another proof. The main question is how do we go about proving theorems? The question is similar to the question how to solve a given problem in programming. Of course, the answer is that finding proofs or solving problem is not an easy thing. Otherwise, life would be good. There is no specified way to coming up with a proof, but there are some generic strategies that could be. And same that we do in the pumping lemma, that step 1 and step 3, they are always the same. Step 2, it's your call. It depends on you how you will choose. And step 4, how you will partition the string. These will make the difference. So it would be hard that in the exam that like 2 students, they have the same. But what I'm looking for at the end to prove that this language is regular or not regular. Today, since I see there is an important need to add this topic to our course, we will review some of these strategies that will be sufficient for this course. The best way to get a feeling of how to come up with a proof is by solving a large number of problems. So go and solve a huge number of pumping lemma. The web is very rich with these examples. Try to solve it by yourself, then you will get used to it. Because next time, we have pumping lemma for something else that we will partition the thing to 5 things and we pump 2 parts. So try to practice yourself solving pumping lemma for regular languages, because in some next handouts we'll have pumping lemma for something else. It is related, however, it would be a bit different. So here I'm giving you some useful tips that you may take a look at the book, How to Solve It by GP. Read and completely understand the statement of the theorem to be proved. You have to understand what you are trying to prove. Most often is the hardest part. Sometimes theorem contain theorem inside them. There is a theorem that contains another theorem. For example, a property of A if and only if a property of B. What does that mean when we say if and only if? If a property A is true, then a property B is true. If a property B is true, then a property A is true. This is the meaning of if and only if. You can work from both sides. Another example is the theorem set A equals set B. To prove this, we need to prove that A is contained or equal to B and B is contained or equal to A. That is, we need to show that each element in a set A is in a set B and vice versa. Try to work out a few simple cases of theorem just to get a grip on it. Crack a few simple cases. This is generic thing for any theorem you might have or you need to prove. Try to write down the proof once you have it. This is to ensure the correctness of your proof. Often mistakes are found at the time of writing. Finding a proof takes time. We do not come prepared to produce proofs. Be patient. It's difficult at the beginning. Think, express, and write clearly, and try to be precise as much as possible. In a few slides, we will go through some of the proof strategies. Direct proofs. The simplest way of proof in mathematics is the direct proof. For example, theorem 1, if n is an odd positive integer, then n squared is odd as well. 2 squared equal 4, it's odd. And so on. Proof an odd positive n can be written as n equal to k plus 1 for some integer where k is greater or equal to 0. Then n squared equal to k plus 1 squared, and in math we know that it will be 4k squared plus 1 squared plus 2 times 2k, which is 4k plus 2. So 2 times 2k squared plus 2k plus 1, since 2k squared plus 2k is even, and even plus 1 is odd, we can conclude that n squared is odd, and we call this a direct math or direct proofs. Proofs by contradiction, the same way that we are proving pumping lemma. This is how a proof contradiction looks like. Theorem 2, statement S is true. The proof, start with assumption. Assume that statement S is false. Then derive a contradiction, such as 1 plus 1 equal 3. In other words, show that the statement not S false is true. This is sufficient because the contrapositive of the statement not S lead to false is the statement true S. The latter logical formula is equivalent to S, and that is what we wanted to show. And if you see in pumping lemma, we assume it's regular, then we prove that it negates one of the regular languages properties, then it's not regular. This is what we call by contradiction. Example, theorem 3, let n be a positive integer. If n squared is even, then n is even. We will prove that theorem by contradiction. So we assume that n squared is even, but n is odd. Since n is odd, we know from theorem 1 that n squared is odd. This is a contradiction. We depend on theorem 1. The pigeonhole principle. This is a simple principle with surprising consequences. Pigeonhole principle, we explained it. More proof techniques associated with example are available in the textbooks, pages 7 to 18. You can read those. The pumping lemma and non-regular languages. We have seen that in the class of regular languages is closed under various operations, and these languages can be described by deterministic and non-deterministic finite automata and regular expression. Pumping lemma, again, these are the assumption. In words, the pumping lemma states that by replacing the portion y in S by 0 or more copies of it, the resulting string is still in a language A or not. This is what we are trying to prove. Read and practice the example in your textbooks, paging 69 to 76. 1 or 2 more example will be solved in the tutorial. So this is an old, since 2020, I added these slides. So in the next tutorial, you will have also 1 or 2 more example about pumping lemma. The TA will solve this question. Good luck for all. Thank you for today. If you don't have a question, you can leave. If you have a question, you can wait and ask your question. Brandon, what do you mean by your question?
Hi, can you hear me?
Yes.
Oh yeah, I was just wondering if you can give us like a schedule as to what you would be covering in each lecture. Because I know that you say that, or I know that you say what we're gonna cover in each next lecture, but like just in case some people miss a lecture or like a Zoom, then they know which
The
material to cover.
handout will show you what will we cover till the end of the term, and I'm going them in sequence. So if you
Okay.
see that, but in this week we'll take this. Sometimes we'll have more questions, so we delay something. Sometimes we finish early. Then
Yeah,
we
yeah.
take one thing.
Okay, yeah. Oh,
Proposal.
sorry.
But for the topics, I'm not sure. Did I put all handouts because they are ready, so I can add them to OWL.
Yeah, or
What is in there? Let me see.
yeah. All the handouts are on OWL, but I was more specifically referring to like which handouts you're going to be covering in each lecture.
Handout 5.
Yeah.
Yeah. So you know the reason because last year I add them all at once. Then
Okay.
the student get mixed. More specifically with midterm, they think that all handout, the 11 handout, is for the whole course.
Okay.
We have 11 handout plus 5A, the one I discussed today, which is 12 in total. So they get confused what is covered, what is not. So what is in there now, this is the midterm material.
Okay.
So as of handout 6, it is outside midterm material.
Okay.
Yeah, so but for example, let me share my screen again. Share. And where is the course and outlines here? So if you see that the first topic is regular language, which is deterministic, finite, automaton, regular expression, non-deterministic, regular, prove a language is not regular, we're still here. Next handout, we'll start with context-free grammars. And here we'll use the pumping lemma again, that it's not context-free, but with 5 portions. Then we'll use recursively embedded decidability and computationally, then the complex theory. So we're still here.
Okay. I was more so referring to like if you could say, or hold on, if you could say like, oh, on like say next Wednesday we'll be doing this handout, or like we'll be covering up to like halfway point of this handout, and then we'll be looking at class note X, for example. Like, do you know what I mean?
Oh, I see.
Or is that possible? Yeah, just in case like somebody misses a lecture, then they know which material to cover for that day. If that makes sense to you?
Yeah, that makes sense. Yeah, sure.
Yeah. And
so
then
next week we will start with handout 5.
Okay.
And we will be done with handout 5.
Okay.
So the context-free grammar, and for the class note, I believe I put them all in our class notes. We are in 6. Let's see, 7. Yeah. So context-free grammar. So you can look for class note number 7 and handout 5.
Okay. Is there any way that you can make that announcement like weekly? Is that possible, or
you know,
if you can, but if not, it's
I don't want a student, you know, a lot of announcements, they will not. I have a bad experience with a lot of announcements.
Yeah, for sure.
They said We have a lot, we get confused, we don't read, we don't notice this. But every
Okay.
class I will announce what we'll get next.
Okay. Yeah. Okay. I was wondering if you could like do an announcement or like a document that would have like a schedule. But yeah, no, that's okay.
Yeah, because for assignments, midterm, group assignments, tutorials date, we can work on those, and I announce the schedule. But what we will cover as a material, because sometimes with certain material that group of students didn't understand, we might spend like a week and a half. However, in my plan, it was a week or less.
Okay.
So for me, I don't like strict myself with, oh, and this week I have to end handout 7.
Oh, okay. That
What
makes
I will
sense.
do if a student don't understand handout 6, no, I'll keep repeating handout 6 till I make sure that the majority of the student or all students understand what I'm saying. So
Okay.
for me, it's not a matter of how many handouts we are done, rather than do the student understand what I'm saying or not? This is the most important part. I need you to understand the concept, the thing. It's better than like finish 12 handout and 50% of the students don't understand half of them, rather than finish 6 of them and all the students understand 90% of the curriculum.
Yeah, for sure.
Yeah, so this is my way of teaching. But every class remind me what we'll take next.
Okay, yeah, for sure. Yeah, thank you so much.
You are welcome.
All right, have a good weekend.
You too. Bye for now.
Yeah, bye-bye.
Tai, you have, Chen, you have a question? Okay, we'll stop here and see you next week.